Welcome to the series of e-learning modules on replacement model for items which deteriorate with time. By the end of this session, you will be able to realize the need to study replacement and maintenance analysis techniques, apply replacement policy for items whose efficiency deteriorates with time and for items that fail completely. Now first let us start with an introduction. The problem of replacement is felt when the job performing units such as men, machines, equipments, parts, etc. become less effective or useless due to either or sudden or gradual deterioration in their efficiency, failure or breakdown. By replacing those with new ones at frequent intervals, maintenance and other overhead costs can be reduced. However, such replacements would increase the need of capital cost for new ones. Example 1. A vehicle tends to wear out with time due to constant use. More money needs to be spent on it on account of increased repair and operating cost. A stage comes when it becomes uneconomical to maintain the vehicle and it is better to replace it with a new one. Inference. Here, the replacement decision may be taken to balance the increasing maintenance cost with the decreasing money value of the vehicle with the passing of time. Now coming to the second example. In case of highway tube lights, where time of failure is not predictable for individual tubes, they are replaced only after their individual failure. However, it may be economical to replace such tubes on a scheduled basis before their failure. Looking into the inference, here the replacement decision may be taken to balance between the wasted life of a tube before failure and cost incurred when a tube completely fails during service. Thus, the basic problem in such situations is to formulate a replacement policy in order to decrease an age or period at which the replacement of the given machinery by equipment is most economical, keeping in view of all possible alternatives. In this session, we shall discuss the replacement policies in the context of the following three types of replacement situations. First, items such as machines, vehicles, tires, etc. whose efficiency deteriorates with age due to constant use and which need increased operating and maintenance cost. In such cases, the deterioration level is predictable and is represented by increased maintenance or operational cost, its waste or scrap value and damage to item and safety risk. Items such as light bulbs and tubes, electric motors, radio, television parts, etc., which do not give an anticipation of failures to specify the probability of failure for any future time period. With this probability distribution and the cost information, it is desired to formulate optimal replacement policy in order to balance the wasted life of an item replaced before failure against the costs incurred when item fails in service. The existing working staff in an organization gradually reduces due to retirement, death, retrenchment and other reasons. Now coming to replacement of items whose efficiency deteriorates with time. When operational efficiency of an item deteriorates with time, that is gradual failure, it is economical to replace the same with a new one. For example, the maintenance cost of a machine increases with time and the stage is reached when it may not be economical to allow the machine to continue in the system. Besides, there could be a number of alternative choices and one may like to compare the available alternatives on the basis of the running costs, average maintenance and operating cost involved. In this section, we shall discuss various techniques for making such comparisons under different conditions. While making such comparisons, it is assumed that suitable expressions for running costs are available. Model 1. Replacement policy for items whose running cost increases with time and value of money remains constant during a period. The cost of maintenance of a machine is given as a function increasing with time whose scrap value is constant. If time is measured continuously, then the average annual cost will be minimized by replacing the machine when the average cost to date becomes equal to the current maintenance cost. If time is measured in discrete units, then the average annual cost will be minimized by replacing the machine when the next period's maintenance cost becomes greater than the current average cost. Now coming to the proof. The aim here is to determine the optimal replacement age of a piece of equipment whose running cost increases with time and the value of money remains constant, that is, value is not counted during that period. Let C equal to capital or purchase cost of new equipment. S equal to scrap or salvage value of the equipment at the end of T years. R of T equal to running cost of equipment for the year T. N equal to replacement age of equipment. When time T is a continuous variable, if the equipment is used for T years, then the total cost incurred over this period is given by TC equal to capital or purchase cost minus scrap value at the end of T years plus running cost for T years, which is equal to C minus S plus integral 0 to n of R of T into dt. Therefore, the average cost per unit time incurred over the period of n years is ATC of n is equal to 1 by n into C minus S plus integral 0 to n of R of T into dt. This is represented as equation 1. To obtain the optimal value n for which ATC of n is minimum, differentiate ATC of n with respect to n and set the first derivative equal to 0. That is, for minimum of ATC of n, differentiation d by dn of ATC of n is equal to minus 1 by n square into C minus S plus R of n by n minus 1 by n square integral n to 0 of RT into dt is equal to 0, or Rn is equal to 1 by n into C minus S plus integral n to 0 of RT into dt, where n not equal to 0 and it is represented as equation 2. Hence, the following replacement policy can be derived with the help of the second equation. Policy: replace the equipment when the average annual cost for n years becomes equal to the current by annual running cost. That is, Rn is equal to 1 by n into C minus S plus integral n to 0 RT into dt. When time t is a discrete variable, the average cost incurred over the period n is given by ATC of n is equal to 1 by n into C minus S plus summation RT, which is represented as equation 3. If C minus S and summation RT are assumed to be monotonically decreasing and increasing respectively. Hence, there will exist a value of n for which ATC is equal to minimum. Thus, we shall have inequalities. ATC of n minus 1 greater than ATC of n less than ATC of n plus 1, or ATC of n minus 1 minus ATC of n greater than 0, and ATC of n plus 1 minus ATC of n greater than 0. Equation 3 for period n plus 1, we get ATC of n plus 1 is equal to 1 by n plus 1 into C minus S plus summation RT is equal to 1 by n plus 1 into C minus S plus summation RT plus R of n plus 1. Therefore, ATC n plus 1 minus ATC of n is equal to n by n plus 1 into ATC of n plus A of n plus 1 by n plus 1 minus ATC of n is equal to R of n plus 1 by n plus 1 plus ATC of n into n by n plus 1 minus 1 is equal to R of n plus 1 by n plus 1 minus ATC of n by n plus 1. Since ATC of n plus 1 minus ATC of n greater than 0, we get R of n plus 1 by n plus 1 minus ATC of n by n plus 1 greater than 0. R of n plus 1 minus ATC of n greater than 0 or R of n plus 1 greater than ATC of n, which is represented as equation 4. Similarly, ATC of n minus 1 minus ATC of n greater than 0 implies that R of n plus 1 is less than ATC of n minus 1. This provides the following replacement policy. Policy 1. If the running cost of next year, R of n plus 1 is more than the average cost of nth year, ATC of n, then it is economical to replace at the end of n years. That is, R of n plus 1 is greater than 1 by n into C minus S plus summation R of t. Policy 2. If the present year's running cost is less than the previous year's average cost, ATC of n minus 1, then do not replace it. That is, R of n less than 1 by n minus 1 into C minus S plus summation R of t. Let us take an example to understand this model. A firm is considering the replacement of a machine whose cost price is Rs 12,200 and its scrap value is Rs 200. From experience, the running, maintenance and operating costs are found to be as follows. When should the machine be replaced? First row represents the year 1 to 8. Second row represents running cost. Now coming to the solution. We are given the running cost R of n, the scrap value S is equal to Rs 200 and the cost of the machine C is equal to Rs 12,200. In order to determine the optimal time n when the machine should be replaced, we first calculate the average cost per year during the life of the machine. The calculations are shown in the table. First column indicates the year of services of the machine from 1 to 8, and in the second column we have taken the values of the running cost. In column 3, we indicate the cumulative values of the running cost, that is, the running costs are added up sequentially. Column 4 indicates the depreciation cost, that is arrived by subtracting C minus S, which is equal to 12,000 for all the 8 years. Column 5 indicates total cost, that is the total of the values in column 3 plus column 4. The values in the last column are the average cost which is arrived at by dividing the values in column 5 by the values in the column 1. It may be noted that the average cost per year, ATC of n, is minimum in the 6th year. Also, the average cost in the 7th year is more than the cost in the 6th year. Hence, the machine should be replaced every 6 years. Now coming to model 2. Replacement policy for items whose running cost increases with time but value of money changes with constant rate during a period. Value of money criterion, if the effect of the time value of money is to be considered, then the replacement decision analysis must be based upon an equivalent annual cost. For example, if the interest rate on rupees 100 is 10% per year, then the value of rupees 100 to be spent after 1 year will be rupees 110. This is also called value of money. Also, the value of money that decreases with constant rate is known as the depreciation ratio or discounted factor. The discounted value is the amount of money required at the time of the policy decision in order to build up funds at compound interest large enough to pay the required cost when due. For example, if the interest rate on rupees 100 is R% per year, then the present value or worth of rupees 100 to be spent after n years will be D is equal to 100 by 100 plus R whole to the power of n, where D is the discount rate or depreciation value. After having an idea of discounted cost, the objective should be to determine the critical age at which an item should be replaced so that the sum of all discounted cost is minimum. Let us take an example to understand this model. Let the value of the money assumed to be 10% per year and suppose that machine A is replaced after every 3 years, whereas machine B is replaced every 6 years. The yearly costs in rupees of both the machines are given below. Determine which machine should be purchased. First row indicates the year from 1 to 6. Second and third row indicates yearly cost of machine A and machine B respectively. Moving to the solution. The discounted cost or present worth at 10% per year for machine A for 3 years and B for 6 years is given in the tables below. Table 1 shows that discounted cost of machine A, which is calculated for 3 years as machine A is replaced every 3 years. The first column represents the time period of 3 years, the second column represents the cost of the machine for 3 years, and the next column calculates the present worth of the machine using the formula D is equal to 100 by 100 plus R whole to the power of n. We will get the present worth as 1000 for the first year, 181.82 for the second year, and 330.56 for the third year, which gives a total of 1512.38, and the average yearly cost of machine A is 1512.38 divided by 3, which is equal to 504.13. Table 2 represents the discounted cost of machine B to calculate the average yearly cost for a period of 6 years, as this machine is replaced once in 6 years. In this table, the first column represents the time period of 6 years, the second column represents the cost, and the third column represents the present worth calculated taking into account the discount cost of 10% with dividing it by 10 plus 1, that is 11 to the power of n, that is the time period. We get the values as 1790.91, 165.28, 225.39, 273.20 and 310.45, which gives a total of rupees 2765.23. The average yearly cost of machine B is rupees 2765.23 by 6, which is equal to rupees 460.87. With the data on average yearly cost of both the machines, the apparent advantage is in purchasing machine B, but the periods for which the costs are considered are different. Therefore, let us first calculate the total present worth of machine A for 6 years. Total present worth is equal to 1000 plus 200 into 0.9091 plus 400 into 0.8264 plus 1000 into 0.7513 plus 200 into 0.6830 plus 400 into 0.6209 is equal to rupees 2648.64. This is less than the total present worth of machine B. Thus, machine A should be purchased. Now next, coming to present worth factor criterion. In this case, the optimal value of replacement age of equipment can be determined under the following two situations. The running cost of an equipment that deteriorates over a period of time increases monotonically and the value of the money decreases with a constant rate. If R is the interest rate, then present worth factor PWF is equal to 1 plus R to the power of minus n. It is also called as the present value of 1 rupee spent in n years from time now onwards. But if n is equal to 1, the present worth factor is given by D is equal to 1 plus R to the power of minus 1, where D is called the discount rate or depreciation value. The money to be spent is taken on loan for a certain period at a given rate under the condition of repayment in installments. In replacement of items on the basis of the present worth factor includes the present worth of all future expenditure and revenues for each replacement alternatives. An item for which the present worth factor is less is preferred. Let C is equal to purchase cost of an item, R is equal to annual running cost, N is equal to life of the item in years, R is equal to annual interest rate, S is equal to scrap or salvage value of the item at the end of its life. Then the present worth of the total cost during n years is given by total cost is equal to C plus R into PWF for R percentage interest rate for n years minus S into PWF for R percentage interest rate for n years. If the running cost of the item is different for its different operational life, then the present worth of the total cost during n years is given by total cost is equal to C plus R into PWF for R percentage interest rate for I years minus S into PWF for R percentage interest rate for I years, where I is equal to 1, 2 up to n. Now next, coming to general cost function. If the maintenance cost increases with time and the money value decreases with constant rate, that is the depreciation value is given, its replacement policy would then be based on the following. Replace if the running cost of next period is greater than the weighted average of previous cost. Do not replace if the running cost of the next period is less than the weighted average of the previous cost. Coming to the proof. Suppose that the item, that is the machine or equipment, is available for use over a series of time periods of equal length, say 1 year. Let us use the following notations. C is equal to purchase price of a new item. R of n is equal to running cost of the item at the beginning of nth year. R of n plus 1 is greater than R of n. R is equal to annual interest rate. D is equal to depreciation value per unit of money during a year 1 by 1 plus R. Let us assume that the item is replaced after every n years of service and has no resale value. The replacement policy can be formulated by calculating the total amount of money required for purchasing and running the item for n years. The period for which the total money is minimum will be considered best. The present worth or discounted value of all future costs of purchasing and running the item with the policy of replacing it after every n years is given by d of n is equal to c plus summation d to the power I minus 1 into r of I into 1 by 1 minus d to the power n into sum of infinite GPD less than 1. It is represented as equation 5. The value of d of n in the equation 5 is the money required to pay all future costs of purchasing and running the equipment with the replacement policy of every n years. Obviously, the minimum value of d of n will be preferred. In other words, if n is an optimal replacement interval, then d of n will be minimum because of the inequality d of n plus 1 greater than d of n less than d of n minus 1. From this, two inequalities d of n plus 1 minus d of n greater than 0 and d of n minus d of n minus 1 less than 0 can be established. The condition for minimum value of d of n can be expressed as d of n minus d of n minus 1 less than 0 less than d of n plus 1 minus d of n, which can be written as 1 minus d to the power n by 1 minus d into r of n minus p of n less than 0 less than 1 minus d to the power n by 1 minus d into r of n plus 1 minus p of n, which is also written as 1 minus d of n by 1 minus d into r of n less than p of n less than 1 minus d of n by 1 minus d into r of n plus 1, which can be written as r of n less than c plus of Rn plus dr2 plus d square r3 plus up to d to the power n minus 1 Rn by 1 plus d square up to d to the power n minus 1 less than r of n equal to 1. This expression between r of n and r of n plus n represents the weighted average W of n of all costs up to the period n minus 1 with weights 1, d, d square up to d of n minus 1 respectively. The given weights are actually the discounted factors of the cost in the previous years. Hence, the value if n satisfying the above relationship will be the best age for replacing the given item. Coming to the summary. Here's a summary of our learning in this session, where we have understood the need to study replacement and maintenance analysis techniques, how to apply replacement policy for items whose efficiency deteriorates with time and for items that fail completely. Thank you.